Okay, here we are going to talk about absolute value equations. Equations that have absolute values in them. We recall what absolute value does to a number. If you have the absolute value of 7, it's going to give you 7. If you have the absolute value of -7, you will also get 7. Absolute values started off by being a way of measuring distances. Whether you're taking the distance from 5 to 8 or 8 to 5, it should end up 3 either way. So absolute value of 15, that's 15. Absolute value of -15, 15. So when we get down to negative, the absolute value of -36, we get that this part right here is 36 with a negative sign in the front, just like that. So we look at how to deal with equations that have this in it. Easiest one, absolute value of x equals 7. Now absolute value takes a negative number and a positive number and puts them in the same place. So the opposite of doing absolute value is to look backwards and say, okay, what numbers could be made positive to equal a 7? And we see that it splits into two separate answers. You could either have x equals a -7 or x equals a +7. Or x equals a +7. Another one, y, absolute value of y equals 10. This would split into y could equal a -10 or y could equal a +10. And while we're looking at this, there's one thing that you've got to understand about absolute values that's kind of nice. That if you ever have an absolute value like this and it equals, say, a negative number like -4, then there's no way that this positive number can ever equal a negative number. It just can't happen. Done. No solution at all. So let's try one over here. If I have something like absolute value of 2x minus 5 equals 10. This is going to split so that the 2x minus 5 could equal a -10, or we could have the 2x minus 5 equals a +10. And we just solve these two equations individually. Add 5 and divide by 2. And over here, add 5, divide by 2. And there we have those two solutions. Now sometimes you'll get an absolute value equation that looks something like this. 3x plus 8 equals absolute value of 2x minus 7. Something like that. Now these two numbers are both going to be positive on either side of the equation because of the absolute values. So if these two numbers inside the absolute values are equal, even if they're both negative or both positive or whatever, but if they're equal, you'll get an answer. So that gives us this, 3x plus 8 equals 2x minus 7. And that'll give us one answer. The other answer comes if these two are opposite signs, whether one's positive and one's negative, or one negative, one positive, either way. So that's one equation. Here's the other equation. Gives us 3x plus 8 equals the opposite of this, -2x plus 7. And we solve these two equations separately. So subtract 2x, subtract 8, and that gives us one answer. And then over here we have add 2x, subtract 8, divide by 5. Okay, there's absolute value equations.
Now that you've had a chance to see the absolute value equations, where you split them into a negative and a positive one, now we'll give you a chance to look at these 4 problems. To the boards! Give them a try, pause the video, and resume when you're ready to move on. All right, now you've got them in your notebook. Let's see how you did. This splits into a positive and a negative. This x minus 4 equals 13, just like it's written, and x minus 4 could equal a negative 13, and both of these, a 13 in there and a negative 13, absolute value would equal 13. So let's solve these two equations and get our answers. Add 4 to both sides, x equals 17, and if we add 4 to both sides here, we get x equals a negative 9. So our two answers are 17 and negative 9. Number 2. Here we have the absolute value equals a negative. Ooh, automatically bad. This will always be a positive number. Will a positive number ever equal a negative? No. So this one there is no solution. You can never make this work. If you happen to put something on here, then go ahead and try it in there and see if it works. And you'll see that it doesn't. Even if you split it up into negative 5 and 5. The absolute value of negative 5 and 5 is not negative 5. So it won't work. All right, let's try this one. Split it into the normal one, 3x plus 4 equals 1, and the opposite, 3x plus 4 equals a negative 1. Here we go. Subtract 4 and we get 3x equals a negative 3, x equals a negative 1. If we subtract 4 off of this one, we get 3x equals a negative 5, x equals a negative 5 thirds. Yeah, there we go. We now have two answers. And you'll notice that with some of them, you may have started believing you'd always get a positive and a negative answer. That is not necessarily the case, and it could work out this way. All right, number 4. So the split comes, and we have the positive one actually just looks like these two left alone, just like it is. Plus 5 equals 5x minus 1. And you got to leave that as a minus 1, just like this minus 4. When you take them out of the absolute values, remember we're undoing absolute values by splitting the equations. We don't adjust anything inside. So we've got that one, and then 2x plus 5 equals the opposite, or negative, of this whole thing, which is a negative 5x plus a 1. So again, that's a negative of whatever was in there. So now we can solve these together. So on this one, subtract 2x from both sides, and we have 3x minus 1. So that was subtracted 2x, subtracted 2x there. And then add 1, we get 3x equals 6, and we get x equals 2. Yeah, go ahead and check that in there and see if that works. 2 times 2 is 4, plus 5 is 9, equals 5 times 2 is 10 minus 1 is 9. Absolute value of 9 equals absolute value of 9. True. So now we try it with the equaling opposite. We get add 5x to both sides. We get 7x plus 5 equals 1. Subtract 5 and we get 7x equals a negative 4, and x equals a negative 4/7. And just for fun, you could stick this guy in as well. So we get negative 4/7 times 2 is a negative 8/7 plus 5, which is 35/7. So we get negative 27/7. Sticking that in, we get 27/7. Wow, yeah. Over here, 7 times negative 4/7 is negative 20/7 minus 1. So that's minus 7/7 gives you a negative 27/7. Take the absolute value of it, and it's 27/7 equals 27/7. Yeah, both of those numbers will actually work. Nice job. Let's go back and see how we do inequalities.
Having just finished absolute value equations, we are now ready to tackle absolute value inequalities. Which work very similarly to the equations, so we'll start off with what we know. If we were to be given absolute value of x is greater than or equal to 7, say, there are certain numbers that will work here. Before figuring out what we're doing, let's look and see what numbers will actually work. We could have a 8, a 9, a 10, 11, 12, 13, and on up. But also there's another set of numbers, and if we look at them in the number line here, there's another set of numbers that would work. Here's 0, here's 7, here's negative 7 right there. We know that everything bigger than 7 obviously is going to work. But it turns out that these numbers over here, when you make these guys positive, you flip them up that direction over there, and they end up being bigger than 7 as well. So here's another one. If we have something like absolute value of t greater than or equal to 5, then we have two sets, distinct sets of numbers that work. There's 5 and there's negative 5. So certainly all of these guys will work. But these guys right here, -6, -7, -8, because of this absolute value turning them positive, they will also work and solve the inequality. And so we get, whenever these absolute values are greater than a certain number, remember absolute value came from distance. So this absolute value, this distance being bigger than 5, we're looking at all numbers that are further than 5 away from our 0 right here in the middle. So we get this solution. We break it up, instead of just breaking it up into two equations like we did with the absolute value equations, it'll break up into two inequalities. The one looks exactly the same. The other one, when you have the negative, it flips direction. So you have this sort of a thing going on. Now I'm going to do these very similar over here. We're going to have absolute value of x is less than 7. See how that changed when we went from a greater than to a less than symbol. Now the numbers that'll work, if here's 0 and there's 7 and there's -7, less than 7 usually starts like this. So we get the idea: 6, 5, 4, 3, 2, 1, 0. They all work in here because they're already positive. And of course their opposites work in there too. Now as soon as we get down here to -7, we don't work anymore. If we start sticking in -8, -9, -10, you stick them into the absolute value turns them positive, and now it no longer is smaller than 7. So again, we see absolute value representing distance. We're saying distance is smaller than 7 from 0. Well, you can kind of see what's going on here. That this is now on a leash. It's trapped. It's stuck in between 7, -7. And what has really happened is it's split into two things. An x is less than a 7, and an x is greater than a -7. And these two things are now connected with and. So this is the preferred way of writing that compound inequality, with an and, that they join together like that. Let's do this other one down here, very similar. Absolute value of t less than or equal to 5, and t is trapped. Since the absolute values can do it, we're going to break it up into the two inequalities, but we get less than or equal to 5 and greater than or equal to -5 at the same time. If you were to try to do that over here, you'll notice how funny it would look to have t greater than or equal to 5 and less than or equal to -5. You have -5 bigger than 5. So that will, if you ever get confused as to which ones you can write like this and which ones you can write like this, that will be sure to help you. So you can see here on the graph, there's 0, there's 5, and there's -5. And we start right there on 5 and go down to -5, and it's good. Interval notation looks like this. The interval from -5 up to 5. So let's try a couple of them. 3x plus 8 is greater than or equal to 7. This is going to split up into two equations. You can kind of tell because I could start sticking a million or a billion or -1 million, -1 billion, and when you make a positive, you're definitely going to be bigger than 7. So we're going to be shooting off, our answers are going to be shooting off to infinity in both directions. So let's write both of those down. Where 3x plus 8, if it is less than -7, less than or equal to -7, we're going to get an answer here. So if this whole thing turns out to be -8, -9, -10, or -50 billion, when you make it positive, because of the absolute values, it will make it bigger than 7. So that'll give us answers. The next one, 3x plus 8 greater than or equal to 7, just like it's written. Solve these guys. 3x less than or equal to -15, x is less than or equal to -5. Where 3x is greater than or equal to -1, x is greater than or equal to -1/3. No switching of the sign because we did not divide by a negative number. And this is an OR statement because the numbers can be -1/3, -5. The numbers can be down in this area here or up in this area here, and that's a union. So set notation, graph, and interval from negative infinity up to negative 5, union negative 1/3 to infinity. And we'll look at one very similar to that. We'll go 3x plus 8 less than 7. Now this one, the absolute value is contained. It's like kept in on a leash. You can't ever get bigger than 7 once you take these absolute values. So that means you start sticking a million or a billion or a zillion, like this guy shoots off to, and 3 million, when you make it positive, is it going to be smaller than 7? No. What about negative 3 million? When you make it positive? No. So this is, you can kind of sense that it's going to be trapped here, and so it's going to make a compound inequality. 3x plus 8 is less than 7, and 3x plus 8 is greater than negative 7 at the same time. So here we have this compound inequality that we can solve, and if we looked at just this half right here, we would subtract 8, subtract 8. Well, if we looked at just this half here, we would subtract 8, subtract 8. So if we subtract from all three portions of this compound inequality, we still maintain that compound inequality. So we have a negative 15 less than 3x less than negative 1. Now we're going to do a very similar thing with the dividing. Divide by 3, divide by 3, divide by 3, and we are left with x less than negative 1/3 greater than negative 5. You'll notice on the graph here, 0, we still have the negative 1/3 and still have the negative 5, but now it says we are trapped in between them. X is greater than the negative 5 and less than the negative 1/3. So we're stuck right in there, which makes sense with what the absolute value of this is going to be trapped. So here's this. And these are the numbers that when you times them by 3 and add 8, they will be right in between negative 7 and 7. So the interval notation will be negative 5 to negative 1/3. And there we go. Couple of ones that we're going to do here that I'm going to show you. 3x plus 8 greater than or equal to a negative 7. Now back when we did equations, we said, hey, we don't even have to do anything when we have a negative. We automatically have no solution. Well, that's not entirely true here. If we were trying to make this guy equal to negative 7, certainly we can never make a positive number equal a negative number. So that was true back with equations. Absolute values never equal to negative number, and that's still true now. However, this is a positive number, which means it's always bigger than or equal to 0, which means it is bigger than or equal to negative 7. These two will never equal each other, but this guy is always bigger. So the solutions to this, if we mark 0 here, we can mark any number. The solutions are everything. So we could write it like this. The set of all x such that x is a real number. It's on this real line. Everything works. We will always have a positive greater than a negative. So let's try one very similar. Absolute value of 3x plus 8 less than negative 7. Now here, this is positive. It will never equal a negative 7. It's always bigger than a negative 7. It is never smaller than a negative 7. So this is no solution. If it's asked in set notation like this, there is a way to write a set that has nothing, and it is a circle with a line through it. And that is the way they write the empty set. That's what that thing is. And that's absolute value inequalities.
Okay, and now that you've seen how to do inequalities where you split them with the negative, which always switches direction, don't forget to do that, we have a few more problems for you. To the boards! So look these over and pause the video and give them a try. And then resume the video when you're ready to see the answers. So this one splits into two. So we have the x minus 4 can be bigger than 13. And the other one is that x minus 4 is less than the negative 13. Now again, the negative one switches direction. So we have x minus 4 smaller than that. So let's look at the two answers. X greater than 17. Yeah, that works. And x less than a negative 9. Now notice that these two right here, the answers in here can either be bigger than 13 or, so this is an or statement, less than negative 13. So on a graph, it looks like this. There's 0, there's 17 way up there, and there's negative 9 right down there. We have 17 and greater than that, and negative 9, and x is smaller than that, like this. And in interval notation, it would look like this, from negative infinity to negative 9, open, open, union, or is what's happening between these two, and 17 all the way up to forever. There we go. So this is what is called set notation, when you put something like this on and have those nice little things look like that. This is the graph, and this is interval notation. So there are three ways of saying the exact same thing. Number 2. Okay, this is the absolute value of 5x minus 7 is bigger than negative 5. Now we have a negative sign over here, which when it was in equals, positives will never be equal to negatives. They'll never be less than negatives. But since this is positive and that's a negative number, positives are always bigger than negative. So this is actually x is all numbers. Yeah, that's right. No matter what you stick in there, once you take the absolute value of it, it will become a positive number, which is always bigger than negative 5. So we don't even need to solve this problem, but recognize that it's a special case. All right, number 3. This one, we have the absolute value of 3x plus 4 less than or equal to 1. Well, if it's smaller than and it's an absolute value, this gets trapped. 3x plus 4 gets trapped in a compound inequality between 1 and negative 1. So the distance can't shoot off forever, because this number, if it gets too big positive or too far in the negative, when it's made positive, it'll be bigger than 1. So it has to fall in between the 1 and the negative 1. All right, so solving it, we're going to subtract 4, and we're going to do it from all three sides of this compound inequality. So negative 5 less than or equal to 3x less than or equal to negative 3. Divide now by 3, and we get negative 5/3 less than or equal to x less than or equal to negative 1. Now notice this is inherently, by how we set it up, this is an AND problem. Everything that is less than is AND, everything that is greater than will be an OR with absolute values. So that's the set notation. If we put the cute little braces and X thing on there, the graph is going to be exactly where the X's are. Oh, we should note that when we did the negative one, 3x plus 4 used to be less than whatever number was over here. This one is a switching of the sign. Even though it looks like it's pointing the same direction, the 3x plus 4 is on the opposite side of it. So this negative did indeed switch that direction. All right, so here's 0, here's negative 1, and here's negative 5/3. And we are in between them, and it is closed, a closed dot on one side and a closed dot on the other, and those are the symbols for interval notation. So negative 5/3 all the way up to negative 1, closed on that end and closed on that end. Excellent. All right, let's look at number 4. This is back to a greater than, so this is going to be an OR statement where we go 2x plus 5 bigger than or equal to 7, and the negative one, 2x plus 5 less than or equal to negative 7. All right, let's do it. 2x, subtract 5 from both sides, greater than or equal to 2. X is greater than or equal to 1. Let's write that OR in there. And then this guy, 2x, subtract 5, is less than or equal to negative 12. X is less than or equal to negative 6. And again, there's your OR statement. Put the little prettifying there. And what do we have? Yeah, that's set notation. The graph of this looks like, well, there's 0, there's 1, and it's going to be a closed thing that way, going all the way up to infinity. And down here at negative 6, it's again closed and heading that way. with an or. So interval notation looks like this: negative infinity to negative 6, that entire interval. Open at negative infinity, you never actually hit it. Negative 6 is an answer. Or union from 1 to infinity. There we go, from 1 to infinity. Good deal, and that will conclude this lesson. Nice job.